These boxes with the arrows in them are your orbital diagrams. So if you were asked to basically draw a picture of what the electron configuration would look like, this is it, okay? So this is hydrogen, and hydrogen has an electron configuration of 1s1. So we have this box, which is an orbital, and it can hold a maximum of 2 electrons. We draw the electrons as either arrows or half arrows, and underneath it we label it with the subshell that it represents. Okay, so the 1 electron in 1s is simply drawn with that 1 arrow. Typically we point the arrows up before we point them down. Okay, so when you partner them up, like with helium, which is 1s2, these are the 2 electrons for helium. You have one pointing up and one pointing down. It would be deemed incorrect to have the electrons pointing in the same direction, so never have them both pointing up or both pointing down. That's because negative charges repel each other, and this is where that spinning up and spinning down concept comes from. So this one that's pointing up would be a plus 1/2. This one pointing down would be a minus 1/2. Okay? Then as you move on from there, if you're looking at lithium, which goes into 2s because it's got a total of 3 electrons. So down here they're showing you that this is my electron configuration for lithium. Here is my 1s orbital. Here is my 2s orbital. You will always draw 1 box for each s. You will always draw 3 boxes for each p. And then they filled it accordingly. Notice they filled the 1s first, and then they filled the 2s. So now we have a total of 3 electrons. Here for beryllium with the 4 electrons, 2, 1 in 1s, 2, 1 in 2s. You don't have to draw the 2p here because you're not going to use it, okay? But for boron, boron goes into the 2p's. You are required to show all of the orbitals, whether you are completely filling them or not, if you enter that subshell. So you have to have the 1s, you have to have the 2s, and you have to have 3 boxes for 2p. And even though we only have 1 electron, the reason why you have to show them all is because they will ask you questions like, how many singly occupied orbitals do we have? Well, you have 1 singly occupied orbital. Okay, yes?
What about the irregular ones like chromium, copper, silver, and gold? Would you draw the boxes that you take out?
Yeah, so if we're doing chromium as an example, okay, so chromium would have 1s, 2s, 2p, I'm probably going to run out of room, 3s, 3p, 4s, 3d, we end on 1, 2, 3, 4, 5. Okay, so here's chromium. Chromium is 1s2, 2s2, 2p6. Watch how I fill these in because it matters. These are orbitals of the same energy because they're all in 2p. Okay. This is, they're called degenerate orbitals. When you're filling orbitals of the same energy, you have to fill them singly first before you double them up because the electrons want to get far away from each other. So even though I have 6 electrons in 2p, you would fill them singly first, point them in the same direction. Generally speaking, we point them up, and then you would go back and you would point them down. Okay, so 3s has got 1 up, 1 down. 3p has got 6. 4s has got, that's a mistake. 4s has 1, right? Because chromium is an exception. 1 jumps over from 4s to completely or halfway fill 3d. So we would have 1, 2, 3, 4, 5 in 3d. Okay, because chromium is an exception or an anomalous electron configuration. Does that make sense? Yeah? Okay. I think that's it for this section. If you have a hard time figuring out, I don't know, like which subshell to fill first, in your book, they give you a diagram, which is a really good thing to use. Just let me know when you're ready for me to turn the page. Okay, so Hund's rule is what I was following when I was filling the orbitals of the same energy, like a 2p or a 3d, where I filled them singly first and I doubled them up. That's what this definition is. And then this right here. This is really useful for when you get confused and you don't know what to fill next. So you follow the arrows. So this is telling you fill 1s, then fill 2s, then 2p to 3s, and then 3p to 4s. It follows the same order as it does on the periodic table, but that's just really helpful. And then I think that's it. We have covered everything.